Hello and welcome to this video where today we're going to be looking at three different quantities that you can measure in a circuit. We're going to be looking at the current and the potential difference and also the resistance. So we're going to start off with the current in a circuit. So this is a typical circuit. It has a source of potential difference here and it's got a component, which in this case is a fixed resistor here, and we're going to build up a model of actually what happens inside these wires. Now the model is going to help us to visualize what's going on. It's not strictly true, the model that we're going to build, but it will help us to kind of see what's going on and to calculate some of the quantities that we need. So we can start off with current. So if we zoom in on this bit of the circuit, then we could imagine that our wire looks like this. These are the ions. So if this is a copper wire, these are copper ions, and because this is a metal, it's got delocalized or free electrons, and they're basically free to be able to move wherever they want, which is why this thing is a conductor. Now, as soon as we connect this circuit up and we've got a source of potential difference causes a current to flow. So basically what happens is as soon as we connect our potential difference up, it'll cause the electrons to flow all in the same direction in one particular way. So they all start to move in that direction there. So we've got electrons move all together in that direction. Now, when it comes to a circuit, we have a battery that's got a positive and negative terminal, and because the electrons are negative, so these things are negative, we can imagine that if an electron's over here in this wire and this part of the battery is negative, then the electrons are going to be repelled in this direction, so they're going to move this way. And if they're in this part of the circuit, this is positive, which means that they're going to move this way. So electrons move from negative to positive, and you can kind of see why, really, simply because of the charges of the battery and of the electron. Now, quite a long time ago, when people were first studying electricity, they had an idea that something was moving in these wires, but they didn't know what. And they thought, right, it's going to go one way, so we're going to define it to go from positive to negative. So basically, they made a choice. The choice they made was basically completely wrong, but in all textbooks and everything, when you talk about the direction of current, often we talk about the direction of conventional current. So conventional current is describing the current flowing from positive to negative. In reality, what's happening is the electrons are flowing from negative to positive, but we don't normally talk about that. So this kind of sums this up. So conventional current is said to travel from positive to negative. So that if we talk about current flow, that's the direction that it goes in. That's not what happens. In reality, it goes the opposite way. It's just that we're choosing to describe it in this particular way. Basically, people couldn't be bothered to change the textbooks and the equations, so they've kept them all the same. So we're going to work with this conventional current, but it's important that you know this. Now, in order to measure a current, we use an ammeter, and an ammeter goes in series, as we'll see a little bit later on. So in order to measure the current, what we would do is we would draw a line down here, and what we would do is basically count the number of electrons that go past it. In actual fact, we're not really counting the number of electrons. We're actually measuring the amount of charge that goes past this point of the wire. And if we measure the amount of charge that goes past every second, then that's the current. And that's basically what this says. So current is the rate of flow of charge. Basically, it's how much charge flows every second, which is summed up in this equation. This thing here is the current. So, my pen doesn't work. So that's the current, which is measured in amps. This is the amount of charge that flows past this point over here. So that's the charge, which is measured in coulombs. And this is the time, which must be measured in seconds. So that's time in seconds. So if you know the charge that passes this point, and you know how long it takes for that charge to pass this point, then you can work out the current, which is measured in amps. So basically, you could say that 1 amp is essentially the same as 1 coulomb per second. Now, so let's do a little problem involving this equation. So this is my equation that we've just seen. We've got a component like our resistor, and it's got a current of 0.45 amps passing through it. I would like to know the charge that passes through it in 3 minutes, and then once I've done that, how many electrons pass through it. So the first thing I need to do is this thing here. So this is in minutes, and I don't want minutes. I need time to be measured in seconds. So to convert it into seconds, I just multiply by 60. So 3 times 60 is just 180, so I get 180 seconds. I want to know what this charge is. So if I rearrange my equation, I get my charge is simply equal to the current times by the time. If I put my numbers in, the current is this. So the current's 0.45 amps times my time, which we've worked out to be 180 seconds. And if I do that on my calculator, I end up with a charge of 81 coulombs. So 81 coulombs of charge pass that point in my wire every second. Now I also want to know how many electrons pass through my component, but I know the charge in total, and I also know that one electron has got a charge of 1.6 times 10 to minus 19 coulombs. So that's a charge of one electron. So if I divide this number by this number, it'll tell me how many electrons I've got. So my number of electrons is equal to 81 over 1.6 times 10 to minus 19 coulombs, and if I do that then to two significant figures, I get 5.1 times 10 to the 20. So that tells me how many electrons pass through that component just in 3 minutes. Now in order to measure the current, I need an ammeter. So an ammeter measures current. So this is an ammeter. And if I want to know the current going through here, then I must put my ammeter in series with that. In other words, it's in the same part of the circuit as my resistance, as my resistor in this case. So that's basically what this says. Ammeters they must always be connected in series, because what I'm really doing is I'm putting something in here basically to measure the amount of charge that goes past here every second. So that's basically current. Now, potential difference. Potential difference is often thought of to be a little bit trickier. Now, potential difference is related to the energy in the circuit. So as the electrons come back they go around this way, the opposite way to conventional current. As they come back through the battery, they pick up some energy. So some of the chemical energy in here is converted into electrical energy. So you can kind of think that some of this energy is given to these electrons. So you could imagine here that they gain some energy. So they gain energy here. So they've got this energy around here, and then in order to get through here, because this thing's got a resistance, and we'll define resistance in a minute, we have to push the electrons through here. So we have to do some work. So we have to do some work in order to push the electrons through here. And when we do some work, we transfer energy. So the energy that these electrons have picked up here is transferred to this resistor. And then when they come out the other side, basically all of that electrical energy they picked up as they went through the batteries transferred here. So on here you've got electrons with energy, so they've got energy on this side. You can imagine that they don't have any energy on this side because it's all been transferred here. Now this is where our model falls down. This isn't what happens at all. And until we start to look at electric fields in year 13, we can't accurately describe what's going on, but this kind of gives you an idea that as this electron goes through here, it goes through the battery, it'll pick up some energy, it'll travel along. When it gets to here, the energy it's picked up is then transferred to here. So if you think about it, we have a difference in energy on one side of the circuit to another. Here we've got some energy, here we've got electrons with no energy, so we have a difference. So this is where the word potential difference comes from. And rather than thinking about the energy of this electron and this electron, we think about the energy of groups of electrons. In other words, a coulomb of charge. So basically, potential difference is it's the amount of work done. So basically, the amount of energy per unit of charge that we give to this component, give to this resistor. So we can sum it up in this equation. So this here is the potential difference. Okay, sometimes it's called voltage. That's a kind of a common term for it. Examiners will always call it potential difference, but it's measured in volts. This is the work done. So that's the work done, which is basically the same as the energy transferred. That's measured in joules. And this thing is the charge again, which is measured in coulombs. So if we know the amount of charge that passes through here, and we know how much energy is transferred to it, then we can work out the potential difference. And again, we can say that if we look at the units, 1 volt is equal to 1 joule per coulomb, like that. Okay, so let's do a little problem. A very simple problem. I know the potential difference across the lamp is 5 volts, so I've put a voltmeter across it and I've measured the voltage or the potential difference. I want to know the charge passing through the component if the lamp transfers 20 joules of electrical energy every second. So here's my equation. I want to know the charge again, so that's Q. So Q will be equal to W over V. If I rearrange this equation, now W is my work done, which is 20 joules, and the potential difference is simply 5. So in other words, I end up with 4 coulombs. So in other words, there are 4 coulombs of charge passing through this each second. Okay, so that's basically how we use that equation. Now, in order to measure the potential difference, we use a voltmeter, which is this thing here. And because we're now looking at differences in energy on this side of the circuit and this side of the circuit, we must connect this. We need to measure basically the energy per coulomb on this side and also the energy per coulomb on this side, and look at the difference between them, because that's what we're really looking at. So we're looking at the difference between these, which is why this is in parallel. So we say this is in parallel because it goes around this. It's a separate, it's not in this main part of the circuit, it's in a separate part all of its own. So this is in parallel, and that's the reason why, because we're looking at these differences. So that sums it up. So voltmeters are always connected in parallel, so we can look at the difference in energy on this side and on this side, and then work out the difference between it per coulomb. So the final thing we want to have a look at is the resistance. So we've seen that if we have a source of potential difference, it'll make the electrons go in one particular direction. But as they travel along, some of these ions are going to get in their way. And the more they get in the way, the more difficult it's going to be for these electrons to travel along. And so because they get in the way, they resist the current. In other words, they get in the way of the current. So that's basically what resistance is. It's a measure of how difficult it is for a current to flow. Basically, if you have a big resistance, the current's going to find it very difficult to flow. So a big resistance, if we have a big resistance, then you get a small current, small I, and vice versa. If you have a small resistance, then you end up with a big current, simply because if the resistance is small, these don't get in the way very much, and so it's easy for the current to flow, so you get a bigger current. Now there is an equation that relates the resistance and the potential difference and the current, and this is it. This is only true for certain components, or for some components at certain times. We're going to look at this in greater detail in the next video, which is Ohm's law. But for many components, this equation is true. So in this case, R is the resistance. So that's resistance, and it's measured in a unit called ohms, which has got this omega symbol. Again, this is the potential difference measured in volts, and this is the current, I, which is measured in amps. So if we can measure the potential difference using our voltmeter, and we measure the current using an ammeter, and we do potential difference divided by current, then we can calculate the resistance of the component that we've put the voltmeter around. So, our very last problem, if we know the potential difference across a component is 230 volts, and the current through the component is 10 amps, I want the resistance. So this is a very simple problem. R equals V over I. The potential difference is 230, and the current is simply 10, and if we work that out, then we end up with 23 ohms. So the resistance of this is 23 ohms. So that, in a nutshell, is basically resistance, and we've also looked at current and potential difference. In the next video, we'll look at resistance in greater detail, and we'll look at Ohm's law and what happens when this equation isn't true. So thank you very much for watching, and I'll see you again soon.